As with any other matrix operation, we should see how the transpose fits into the algebra of matrix operations. So in other words, how it combines with other matrix operations. One thing that we should check is what happens if you combine the matrix transpose with itself. In other words, what happens if you do the transpose twice. So the first transpose is, so if A is Aij, then the A transpose takes these entries and just switches how they're arranged, so interchanges rows and columns, and then the double transpose, well, that just switches them back. So this is Aij again instead of Aji. So the double transpose is the original matrix. Okay, this is kind of like the negative of a negative is a positive, except it's the transpose of a transpose is the original. All right, so that's not very surprising, I guess. This also makes sense in terms of reflecting the matrix across its diagonal, because if you reflect twice, you get back to where you started. All right, so what about addition and the scalar product? Rather than thinking about addition and scalar product separately, we can do them at the same time just by thinking about what is the transpose of a scalar times a matrix A plus another scalar times a matrix B. So, right, the matrix A, we could write this as Aij. The matrix B we could write as Bij. So let's take the transpose of this. Well, we need to, first I guess we need to figure out what this is. We have to write the stuff in parentheses as a single matrix. So let's do our scalar multiplication by moving the scalars inside. That is what scalar multiplication looks like in terms of entries of a matrix. So that gives us R Aij plus S plus SBij. Okay, now we're going to take the transpose, but again, we have to write the stuff inside the parentheses as a single matrix. So we need to do this matrix addition. So that gives us Raij plus SBij transpose. Now we can do the transpose. And the transpose just switches the indices. So now it's Raji plus SBji. And then, just like we put all these matrices together into a single matrix, we can now tear them back apart. And this is Raji plus S times Bji. But this is just R times A transpose plus S times B transpose. So the short version of this is the transpose operation sort of distributes. I say sort of because the transpose isn't a multiplication, and really we only use the word distribute for a multiplication, but it looks similar. All right, let's see what transpose does to multiplication. So this one is a little trickier because the formula for matrix multiplication is trickier. So this is, let's see, Aij times Bij transpose. So this is, right, we need to write the stuff inside the parentheses as a single matrix. So we have to write down the formula for the entry of a matrix product. So that's sum from k equals 1 to n of Aik Bkj. So we're going to take the transpose. And remember, in this formula for the entry of a matrix product, this I, this is the row index. And this j, this is the column index. So when we do the matrix product, it's the row and column indices that switch. So what we get is so the I and the j switch. So this j is now over here. Ajk Bki. Okay, so this is the result, and you can see that this is, it's not totally clear what this is. One thing that this isn't is some product like this, right? Because the indices are just in the wrong place for it to be a product like this. But it's clearly some kind of product because, right, we have this matching index k with the sum over k. So what is this a product of? Well, this AJK, it's strange to have the summing index in the second position because the first index is not a row index, it's a column index. It would make more sense if this j, which is a column index, were in the second position, but it's not. Well, except, right, AJK, this is actually this is the JK entry of A, but that means it's the KJ entry of A transpose. Right. Similarly, this BKI, this is the KI entry of B, but that means it's the IK entry of B transpose. So this is actually the formula for B transpose times A transpose, right? Because with the entries, right, these entries with the transposes, these are set up to be multiplied in this order, right? So we have I, K, and KJ, right? So it's this formula is actually that matrix product. So matrix multiplication and the transpose kind of hits both matrices, but it actually also switches the order that they're in, which is a little bit weird. This, we'll see, this isn't the only matrix operation that does this, but this is essentially because sort of the conceptual reason why this happens is if you had a vector and two linear vector functions like this, right? So we have this vector x, and first we do the linear vector function b, and then we do the linear vector function a. If you switched all of this to row vectors by doing a transpose, right, we know that the first linear vector function that happens has to show up to the right of x, but the first linear vector function should be the linear vector function represented by b. But the row linear vector function that corresponds to b is the transpose of b, so like this. And then afterwards, that is even further to the right, we have to do the linear vector function corresponding to a, and that's A transpose. So you see, they reverse order because they happen on the right for row vectors instead of on the left. So that's another reason why these have to be in this order. All right, well, now that we have some algebraic properties for the transpose, we could use the transpose to do some algebra like this. We could simplify this expression just using the properties, all of the algebraic properties of the matrix operations. So let's see. To simplify this, I guess for this first part, we're going to have to compute this transpose because we want to do this matrix multiplication, but we can't with this transpose in the way. So let's do this transpose. So we get A transpose plus 2 times B transpose. So that times A plus B minus, and for this part, remember the transpose of a product is the product of the transposes, but in the reverse order. So this is B transpose times A transpose transpose. But A transpose transpose is just A. All right. Now we can do this matrix product. But remember, when you're distributing this matrix product, don't accidentally reverse the order of any of the multiplications. Since the transpose versions are on the left, they will stay on the left when we multiply this out. So we get A transpose A. So that's first times first, and then A transpose B plus 2B transpose A plus 2B transpose B. And then over here we have minus B transpose A. And so now we can combine the B transpose A terms. We get A transpose A plus A transpose B plus, so we have 2 minus 1, so 1 times B transpose A plus 2B transpose B. All right. Of course, because of all the products in here, not every size of matrix would make this expression make sense. So if A is m by n, A transpose is n by m. So actually this term doesn't matter what size A is. This A transpose A term will always make sense. Same thing for B transpose B. But if A is m by n and B is, let's say, p by q, so B transpose is q by p, and so that means m has to be the same as p. So m equals p, and A transpose is n by m, and so again we see that m has to be p. So A is n by m, and B is q by m. So it turns out that these have to be the same.